Things get tricky when you try to cram too many qubits onto one quantum processor. Is the best way to build a machine with thousands of qubits actually to connect or interconnect many smaller processors together? And can this concept be extended to interconnect several large-scale machines across vast distances? Join us for a look at the technology that might get us to behemoth-sized quantum computing in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CEO of Entangled Networks, Aharon Brodutch. Welcome to the show.
Hi. Yeah, nice to be here.
Yeah, I'm super excited to have you on. I mention Interconnect so often on this show that it could be the basis for a very dangerous drinking game. So before we dive into the amazing potential of Interconnect, please tell us a little bit about Entangled Networks.
We're an early stage startup. We're based in Toronto. And the founders, myself and Ilya, we're both physicists by training. My background is very, very long in quantum computing. And then we have a third co-founder who has done this multiple times before, including building a huge optical telecom company. And we decided to solve the biggest problem in quantum computing. And that problem is trying to scale up, trying to build a huge quantum computer. The only way to do that is to take multiple small quantum computers and connect them together. And we're building everything that's needed to do that.
That's amazing. That's part of the reason why I keep bringing this up. So yeah, let's take a step back and we'll just examine some of the reasons why you want to work on Interconnect. So more than just chaining together those multiple big computers out there, it can help us increase, as you hinted, qubit counts inside individual quantum computers, right? I believe there's already a bottleneck in having too many qubits in one quantum processing unit. You want to talk a little bit about that?
Yeah. So we do have a huge bottleneck. And I always like to use IBM as an example because they have a ton of information that's publicly available. And so if we look at what IBM has and what they advertise, they're big. They have these two big ads. One is we have the Eagle processor. It's 127 quantum computers. And then 127 qubits, sorry. And then I wish it was 127 quantum computers.
Less Q times.
Yeah. They have this other a big advertisement. And very recently, we saw this on Twitter, is the 512 quantum volume, quantum volume of 512, which I would call a quantum volume of 9. They do like to take 2 to the power of the actual qubit count. And that's done on a 27 qubit machine. So that's done on Falcon. And so you're seeing that they have this huge machine. It's 127 qubits, very cool. But actually the best performing one is a 27 qubit machine, which is, from a qubit count 2 generations further back. And so adding more qubits to the machine is just insanely hard. And it's insanely hard for 2 reasons. One is, just add more qubits to the machine and get the controls done. And that's what the 127 qubit machine shows. It shows wow, they can get, all the controls in to get 127 qubits. That's kind of amazing. And it's true. Every single technology will have this kind of problem. Try to control that many qubits. But then you want the qubits to interact. That's fundamental for the quantum computer. But you want them to only interact when you're telling them to interact, and they don't only do that. They start to interact, when you don't want them to do it. It's kind of like packing a ton of kids into a classroom. At some point, noise levels just go up, and the teacher stops being effective. And so we're trying to do both of these things at the same time. It's insane. At some point, you have to say this is an optimal size. Let's start connecting modules together.
Interesting. So you'd have the kids in a bunch of little pods and then the teacher moving between them kind of.
Yeah. I mean, in a school, you want different teachers sitting in different classrooms, right? You don't want all the kids in one giant classroom with the teacher teaching, each group, because they'll start talking between groups. And it's
Yeah,
exactly
that's
the
a
same.
great example. So PsiQuantum, when they talked to us, they talked about this idea of building one large computer from interconnected modules, but they weren't really ready to give any specifics on how many qubits would be in each of those modules. I was thinking, like, would it be 50 in each one? I wasn't really sure. But their goal is 1 million total. So, I mean, you got to think there's going to be a good number of modules in those things. So do you have any thought on what the ideal number of qubits might be per module?
Yeah, so that's a super tough question, and the reason it's so hard is that it just depends on a ton of different factors. And so you're looking at the actual qubits and how they perform. You need to look at the interconnect and how it performs, and you need to think of overheads, because the interconnect does take up some of the qubits, and so you have to take all of these things together. And then also look at the kinds of algorithms you want to run at the end. If you're looking short term, it's NISQ algorithms and kind of small error mitigation techniques. And if you're looking large scale, it's really the quantum error correction code that's running. And you have to optimize everything for that. And then when you look at PsiQuantum specifically, they have had this incredible idea, which is, I think, completely unique in quantum today, which is they were thinking about scale from the get-go and about manufacturing. And so we don't really think that much about manufacturing, if you're looking at sort of most of the companies. And when you think about manufacturing, you're adding this other issue to the equation, which is what's the best size to manufacture before it gets there's a trade-off, which is just about cost, right? The number of defects you have before you have to throw something out. And so, they added that, day one to the equation. And so now you have to think modular. You do not want to manufacture a device that's 1 million qubits. And so, it's definitely very hard to guess what the numbers are, but yeah, a ton of different factors that go into making those decisions.
So would you say it's the type of qubit that represents like the limitation of each module? Like PsiQuantum's photonic, IBM's transmon, but IBM publicly already said that their pathway to 4,000 qubits will involve some kind of interconnect. And I think they're going to roll it out in 3 stages, how they're planning on doing that. But their goal is ultimately to admit that, yeah, they got to have multiple processors working together to create that many qubits. So do you think it's the type also that limits?
Yeah, so the type of qubits will be a huge factor. Not just the type. Not just the type on sort of a big picture. Is it photons? Is it superconducting? Is it ions? It's really the very, very specifics of the system. It's really the specifics of the interconnect and how efficient it is. And if we want to kind of have an idea of numbers, people have been tossing some numbers around, not for photonic, but for ion traps. The number, sort of ideal number, seems to be don't go over 50 ions in a single chain. That just adds too many difficulties, and so you want less than 50. Ideal seems to be around 20 to 30 ions in a single device. But what you can do with ions is you can have multiple chains on a single device, and you can shuttle ions from one to the other. And a lot of companies are thinking about doing that. That's a good first stage. But once you take ions and you literally move them from one side to the other, you can kind of imagine that you don't want to move them too far. And so now you have this big connectivity constrained problem. You're only talking to chains that are very close to you. At some point, that just doesn't scale very well. And so you want to start getting outside of that system optically. And again, numbers that are being tossed around will get to about 1 to 2,000 qubits. let's say somewhere between 500 and 4,000 qubits would be the number before you have to go out optically with ions. I would guess that the lower end is probably the more efficient, but the higher end is probably where people want to start actually doing it, just because of other sort of engineering constraints.
At around that point, you think trapped ion, the only way to go up will be to chain entire computers together, right?
Yeah. So I think with ions, that's the number. With superconducting, like you said, we kind of have numbers from IBM. They do say we'll push up a single module to 1,000, and then they're looking at multiple ways of doing even that. They're thinking of breaking down that module into 3 small modules that are still sort of on the same chip. And then at some point, you have to go into an interconnect. Yeah,
neutral atom is kicking around, going for 1,000 qubits next year too, with their Pascal, for example.
They're super optimistic. The neutral ions, they do expect to get to about 10,000 before going optically. And here is this this trade-off that you need to think about. So it's very possible that they'll reach 10,000, so an array of 100 by 100. But now you've got this grid with interactions that are fairly short distance, and you have to start optimizing. Is 100 by 100 really the optimal size for the processor? Even if it's the biggest one you can aim for, very likely that is not the optimal number. And so they might, initially start trying to reach 10,000, and at some point realize, well, actually, from an architecture point of view, we should have smaller modules. So still unknown. We haven't really seen a ton of developments with neutral ions, although it's an early technology and it's super exciting.
Yeah, so let's dig in a little bit to the difference between interconnect when it's inside and outside. Everyone listening to this has multi-core CPUs in their lives. They have laptops, phones. Those are usually multi-core in some way. Can you explain some of the ways that quantum interconnect inside is different than classical connecting of these CPUs together?
Yeah. With a classical CPU, what you need to do is you need to transmit information from one CPU to the next. There's a bottleneck there. It's slower than the CPU just working on its own, but it's fairly simple. We know very well how to transmit information from one side to the other. With quantum, you have to preserve coherence. So maybe I'll say one word about what that means. Quantum computers, the number of possible states in the quantum computer is exponential in the number of qubits. And what you want in order to really get the power of the quantum computer is you want superpositions of these states, and maintaining these superpositions, let's call that coherence for simplicity. And so what you want is you want to keep maintaining these superpositions as you transmit information. The problem with that is that anything outside the quantum system itself destroys coherence. And so one big thing is measurement. And so you can't measure. But the other big thing is essentially any interaction with anything outside is going to reduce coherence. And so sending information outside your computer and hoping it will reach the other side safely is a problem. You can't copy, so you can't try and keep on repeating until success. You're in big trouble, and that's where entanglement comes to help us. So what you can do is you can create an entangled state. That entangled state is a quantum system that is comprised of 2 subsystems, but they kind of act together. And so what you do on one side kind of influences the other side. What Einstein called spooky action at a distance. It's very hard. It's very dangerous to start playing around with this idea because, it's let's call it a mathematical idea that the physical implications are a bit hard to imagine. But one thing that it allows you to do is it allows you to transmit quantum information across this gap using just an entangled state and without actually moving the quantum information physically around from one point to the next. And one way to do this is quantum teleportation. Again, that uses the entangled state. And so what a quantum interconnect does, very differently from a classical interconnect, it doesn't move information around. Instead, it generates entangled pairs. And so what you want is to generate entanglement between these quantum cores, and then you'll use it later to transmit information.
Okay, and it's the entanglement. I mean, entanglement is basically a core part of doing quantum computing. It's one of the things you need, right? You have to have these things be able to be entangled. So when you're tangling from one processor to another, you are in some ways making them behave as one processor.
That's right. So now they're, in terms of the quantum state can be a superposition of the entire space that includes all the qubits on one processor and the next one.
That's a huge difference, because when you do interconnect with classical CPUs, you're sort of just you're almost like sending answers instead of the working equation, right? If you want to simplify it, you'd be sending that to the next machine. Whereas in this case, right, you can have the two parts of the two CPUs QPUs, I should say, work together. So that's kind of how it is when it's close up. Now, if you wanted to do this farther apart, does anything change? If you want to have, you've got discrete machines, like let's say PsiQuantum does build a 1 million qubit machine with all the modules inside. How would it be different to then connect it to another 1 million qubit PsiQuantum machine? Like, what would that machine to machine interconnect be like? Would it be very different than the close up one?
Yeah, so it's a very different use case from the user's experience, right? When you think of a single computer, from your perspective, right? When you're using your laptop, which is 4 cores, 8 cores, you don't want to keep on thinking, I have an 8-core machine. You want to think, I have a computer, it should work. And so from the user perspective, I will look at this 1 million qubit device, which is built up of 10,000, 100 qubit subsystems. In the case of PsiQuantum, it's also in time, so it gets much more complicated. But let's keep it simple here. You don't want to start thinking about that. And so that entire machine has to work seamlessly as one machine. That is a very different problem from saying I have 2 computers, and what they're doing is they're communicating like I'm communicating with you right now. You still need that entanglement in order to facilitate communication for the same reasons that I explained before. But now you need to think less about rates. You're less worried about. You might be less worried about loss because you don't necessarily need them to be working together, although in some cases you still want the entanglement to be, actually in many cases you still want the entanglement to be there. But it's very different talking to each other than working together as a single machine. And we know this classically, right? It's very different thinking about an internet and thinking about multi-core computing.
Yeah, it's a different kind of bus there. Are there distance considerations when connecting systems like this? Would you be limited by the length of something like a fiber?
Yeah, so definitely distance. Again, we can look at the classical world and see distance plays a huge role. You do get losses as you go longer. When you think about connecting a single computer, the distances are relatively short. And so you deal with losses as you get a little bit further apart, but it's not, end of the world. When you think about internet type communication, losses are going to be a huge problem. And so now you have to put on repeaters, which will allow you to, they replace amplifiers, what would classically allow you to amplify the signal. Repeaters kind of allow you to do long distance. And that's the nice thing about thinking about a small network is, okay, we don't need repeaters. And so distance is less of a problem.
Would it be possible, let's say if it was close together, would it be possible to link computers of complete different type together? Like, let's say a neutral atom and a transmon. Would there be an easy way to do that with the solution you're working on?
Yeah. So, if I would guess what's going to happen in 20 years, I would say quantum computers would not be a single modality. I think there's advantages and disadvantages to each modality, and we will see computers of completely different types working together. But that's long in the future. And the sort of first order reason why it's hard is you need to convert between wavelengths. And so superconducting qubits, they work in microwave. Ions, they work in visible. Even converting between different ions is between the wavelengths of different ions is hard. It's a much bigger challenge to convert from microwave to optical. On the other hand, that challenge has to be met, because if you want to connect multiple superconducting or anything that works in microwave, so the kind of approach that Intel has with solid state, anything that works with microwave, you need to convert microwave to optical if you want to get outside the fridge. And so this is an absolutely necessary technology, for IBM's roadmap. I would say, it's still science. It's not engineering quite yet, but that science has to be solved very, very quickly. And so we'll have the building blocks. Once we have that, we already know how to convert inside optical. Once we have that, it's going to be just engineering, and just engineering it's huge, but we'll make huge strides.
Yeah, so the first system-to-system interconnect we're going to see is most likely going to be of the same type of system, right? It would be two photonic machines or whatever talking to each other, not a mixed bag yet.
Yeah, 100%. I mean, even that. Yeah. If you think about if you think about anything that's not atoms, even that is very hard, because the photons, even if they're the same wavelength, they're not exactly the same. Ions and atoms tend to be different because they're all exactly the same.
So you would think that the most successful interconnect first system to system would probably be trapped ion or neutral atom or something like that first?
Yeah, or diamonds. If they mature as a computing technology, things with atoms inside. Yes.
Cool. Yeah, it's great to get that inside look to how you see the progress mapping out. And your company is going to be publishing a blog. It'll probably be up by the time this hits. You were kind enough to share it in advance. So, I'd love to talk a little bit about some of the results you share in there, and basically, I guess, name this version of Interconnect that your team's working on, and it's called QLink, right?
Yeah. So indeed, our first, our first generation interconnect, we call it QLink A, with a plan of having a B, C, D, etc. version. And that first version will connect two quantum computers together. So you can think of it, again, thinking in terms of classical networking. It's a network adapter. It allows you to extract the information as photons and use that to establish entanglement. And then what we want to do is we want to start educating the world about how we're going to see interconnects in the future, how information gets transmitted across. So we'll have a series of blog posts sort of slowly explaining how these things are going to work. From the very specific protocols, teleportation is one example protocol that can work. There's things that are cleverer and nicer than that. And then we'll show some results both on our plans for hardware, but also on our software, which exists and is running. So one set of results really shows where the advantage is with an interconnect, even if that interconnect is not fantastic. And that's the big problem is currently interconnects are very, very slow. Stuff that has been demonstrated in labs. The device we're building, it's going to be a bit faster than what's been demonstrated, but it's not going to be, orders of magnitude faster, and so you still have to deal with that bottleneck. So we have results showing that even in that case, thinking of today's quantum computers, you're still getting an advantage, and that's not trivial. And then we're also showcasing our compiler. And so what does a compiler for a multi-core system do? It reduces the number of times you want to use the interconnect, because the interconnect is a bottleneck. You don't want to cross that bridge too many times. And we have software that does that extremely well. And so, again, bringing the viability of the interconnect that much closer in terms of what the performance metrics we need are.
I'd love to hear like the good and bad sides, right? So first we'll start with the overhead hit that you're seeing in these initial experiments. Like what kind of, I don't know how what metric you'd want to use, but like what kind of hit are you taking when you do cross that bridge, as you mentioned?
So at the moment, what's been demonstrated in labs around the world is interconnect speeds of about 200 hertz, right? That is very slow. We can reach about 1 kilohertz, or we should be able to reach close to 1 kilohertz on ions. So again, everything is very, very specific to the system, to the underlying system. Ions, they work. A standard 2-qubit gate is about 100 microseconds, and so you're getting about an order of magnitude hit in terms of the time it takes the interconnect to work. It's not great. But it's workable. What we've found is that that you can still operate with that.
Have you already been able to show that with two systems of a certain size, you can see some benefit even with that order of magnitude hit in the transmission?
Yeah. So in simulations, we can show that if you take two small quantum computers, and you use an interconnect, you will get an advantage. So one example that we're going to have out soon is taking two 6-qubit quantum computers, trying to solve a 12-qubit problem on it. And there are tricks to do it. There are tricks where you can try to use those without an interconnect, and you get a certain result. And then you say, what happens if I use an interconnect? Well, in that case, everything's perfect. I have a 12-qubit machine. But what if the interconnect is not perfect? So now you're taking a hit each time you're using the interconnect. And we modeled that, and we still see a huge advantage from using the interconnect. And so if I was to take our design and plug it to a machine today, we would see a performance advantage from using the interconnect.
That's terrific. So if you were to maybe stretch this out a bit on the B, C, D or versions of QLink, you can imagine that if you took two 27-qubit processors, you would see performance that would rival definitely the 127, right?
Yeah. So that's the big catch. Is if I was to take two 27-qubit machines, these two IBM machines, I could probably squeeze a little more power from those machines because they're interconnected. But those, even if I used magic, I would not get the entire 54 worth of qubits. I wouldn't double the computational power just because the processor itself is not there yet. And so what we need is ideally connecting a large number of even smaller processors where each processor is really, really good. That's I think where industry will be aiming very soon is, really getting a ton of computational power from smaller processors. There's, again, a lot of engineering considerations that don't come out in just seeing performance. And this is one of the reasons you're seeing bigger systems is not because you're trying to get more performance, you're trying to test out these new engineering ideas.
So we have to start somewhere, right?
Yeah.
And this approach is beginning. So is there an ideal goal you're shooting for? Like ultimately, like how good do you want QLink to be? So like what kind of overhead losses? Do you envision it being like what speed or whatever? It's hard to extrapolate, I'm sure, with this, but I'm just curious, like what kind of idea you have in mind?
I mean, I think the ideal is you want to be working at roughly the same speed as a 2-qubit gate. You know that's it's never going to be quite as good, but you don't want to be much worse. At that point, it's a bottleneck, but it's not a huge bottleneck. So that's one very, very ambitious goal. That is going to take a while. We don't quite have the physics there yet. So we know how to do it in theory, but no one has demonstrated a working interconnect at those speeds with the kind of requirements that need to be there. For ion traps, it's putting the ions in cavities, for example. And sort of shorter term, we want to see the best performing quantum computer being a multi-core quantum computer. And I think within 5 years we'll be very close to start to show that. So the whatever highest quantum volume or whatever benchmark you're going to take, that will be done on a multi-core machine.
Yeah, it's exciting because within 5 years we expect to see some pretty impressive machines. So pairing up a couple of them might be pretty impressive itself. So a basic timeline, like you would think then that QLink will be sort of commercially out there really within 5 years, right? Is that the idea?
Yeah. So I think, commercially out there will probably before. I think 2025, 2026, if industry timelines are what they're advertised to be, 2025, 2026 is when industry really needs to start linking computers together. Now, from when you start doing it, from when sort of we sell our first product until you've actually built the computer, that takes a bit of time. And so, 5 years we'll be seeing that computer operate at the highest levels. And this is for our technology, which is for everything that's not photonic. If Psi Quantum deliver, and they have an incredible team, we'll see a multi-core quantum computer within a couple of years being the best quantum computer out there. Fingers crossed that they can deliver on promises. Their machine is inherently a multi-processor machine.
Yeah, everyone's really excited to see that one. And I'm excited to see what you guys come up with. You have 25 more letters in the alphabet to go through for your next version. So maybe you'll get lucky and you'll strike gold on the Q version, because that would just be funny, because everyone loves to use that letter. So that's a really great overview of this. Is there anything else you'd like to share before we wrap up?
Yeah, I think, quantum computing is a strange technology in that we're doing a lot of physics. We're starting to do, I think, as industry is growing, we're starting to do a ton of engineering. And so we're doing both of these things in parallel. Getting physicists to think about engineering is not super easy. So we're learning, as we go along. And I think, what we'll see is a bunch of engineering challenges being done in parallel with the physics. For interconnects, that means that we'll see the engineering challenge of getting a multi-core quantum computer to work and deliver results on the one hand, but then on the physics side, get those interconnects to work at the speed that we would like to see where they're not this insane bottleneck on the system.
Thanks so much. I mean, it was really great having an inside look at how this is actually developing and evolving right now, rather than just hearing from the outside. So I'm really glad I got to meet you at IQT, and thanks so much for coming on.
Yeah. Thank you very much for having me on.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Entangled Networks is a startup in Toronto focused on solving the biggest problem in quantum computing: scaling. The company feels the best way to make a high qubit count quantum computer is to connect or interconnect multiple small quantum processors together. The technology can also be used to interconnect those large quantum computers across many miles and yield even greater scale. Imagine connecting 5 1,000 qubit machines, for instance, in different cities, and having them act as one 5,000 qubit system. There is currently a bottleneck when trying to put too many qubits on one chip or processor. Control electronics become difficult to pack, and qubits may experience greater noise levels. Entangled Networks says the best approach is to find the optimal qubit number, build a module with that many qubits, then interconnect them. The optimal number is still up for experiment and debate. Estimates range from 20 to 50 on the lower end to as high as 1,000 to 10,000 qubits on the high end. PsiQuantum is building its computer with an interconnected model, and even IBM admitted some form of interconnect will be needed for its future systems. Classical systems already work with multiple connected cores. Quantum interconnect makes this concept trickier because you have to maintain coherence. Entanglement is used to transmit information by generating entangled pairs between modules and then having the superposition of all the qubits act as one system. The gap between these close-by modules doesn't matter if this is done correctly. Things do get tricky if this is done over quantum networking, with its challenges of repeaters, noise, and losses. In the future, we may be able to interconnect heterogeneous types of quantum computers, like optical and superconducting, but in the near term, Aharon feels this will be difficult. Even sticking to chaining up only the same type of processors, though, the benefits can be huge. Entangled Networks is using something called Q-Link to accomplish interconnect, and published exciting results that already show ways to gain some advantage today. Q-Link interconnect speeds are at about 1 kHz, which is an order of magnitude slower, or a performance hit, on normal 2 qubit gate speeds. But even in this early stage, a demo experiment shows that 2 really optimal 6 qubit machines with interconnect can rival a single 12 qubit machine. So they're on the right track. The goal or ideal is to get interconnect to work at a speed that's close to a 2 qubit gate. Aharon feels that interconnect will be in use within 3 years, and within 5 years, the best performing machines will be built this way. That does it for this episode. Thanks to Aharon Brodutch for joining to discuss Entangled Networks and their work on interconnect. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at ConstantHacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.